I was told I should talk about special classes of graphs. So when we say special classes of graphs, the assumption is that you are already familiar with the general notions of graph theory. So looking at the lectures which are already given here, yeah, you are introduced to many concepts already, right? So I will assume that you know many things, but in case if you don't understand a particular word or something, you can ask, right? So basically I understand, I believe that you're familiar with graphs, and I don't have to tell the key things like what is an independent set, right? What is chromatic number? Such things I'm assuming. So I hope that's fine. Any objection on that? Right. So usually when we say special classes of graphs, somehow people understand a certain type of special classes of graphs, like perfect graphs and the related subclasses is what the main things which are usually told in that. But you may ask why planar graphs, right? But they come in main textbooks, so therefore this topics which are not usually covered in the general graph theory textbooks. Sometimes a small chapter is given to all these things. But perfect graphs and many of its subclasses are the main things which we will cover. After that, some important classes of graphs which do not come in the general textbooks, but which are non-perfect, but still well studied. Right? This is the intention. So if you're doing research in graph theory or algorithms or any related topics, usually it's good to know special class of graphs, because if you have a problem, solving it on the most general case can be very difficult, right? You may not get the answer, you may not get any idea. But on the other hand, working on a special class of graphs may be much more easier because you have much more structure there, right? So therefore you will be able to make progress, and then that may give you some intuition. Maybe that intuition may lead to generalizing those concepts and finally getting the answer to the general case itself possible. Otherwise you at least can prove something for something, right? Because for the most general case there may not be any answer also, right? Many nice theorems may not exist for most general case. You have to do some specialization. So in that sense, for people who are doing research in graph theory, algorithms, related areas, knowing special classes of graphs is always very, very good, because you get many options, right? At least you can try your ideas on some of these things. Otherwise, if you ask me where these special classes of graphs come from, it's not because they are designed for getting some extra structure and working on, it's not designed for PhD students, right? It's not for doing things fast or easier or getting some possibility of trying out, right? Rather, they can come from applications, natural situations. People define it because there are natural situations where they arose from. Sometimes because of some theoretical interest, some people defined it, right? So the one interesting, maybe very interesting special class of graph is perfect graphs. This is where we start these lectures, perfect graphs. This question of perfect graphs comes from the following two parameters: chromatic number, and the other parameter is clique number. So there is, at least for beginners, there is an immediate connection between chromatic number and clique number. What is the connection? Can you talk louder? Clique number is always less than equal to chromatic number. That is an immediate connection, because if I ask you to, I hope all of you understand what is chromatic number. It's the minimum number of colors to vertex color the graph. Clique number is the biggest size, so the number of vertices in the biggest clique. Suppose I tell you that you make a graph, construct a graph with chromatic number greater than 4. What will you do? Can you imagine? Or maybe 5, chromatic number 5 or more. What will be your first?
Clique of size 5 and then.
Yeah, usually that's what people do. So somehow you start with a clique of 5 and then add something if you want something. Otherwise, that itself is enough, right? Clique. Because if you have a clique, you know that to color this graph, now you need 5 colors. Because clique of 5 means all those vertices should get different colors, right? So, I guess that is the only idea which comes to our mind when we try to really construct a graph with a high chromatic number. But that is nowhere near truth. So in fact, this question that is it the clique number that is deciding the chromatic number? I mean, is there a graph whose chromatic number is strictly greater than clique number? This is the first question to ask. Tell me the answer. Are there graphs whose chromatic number is strictly greater than clique number? Because you may suspect that it is the clique number that is causing the chromatic number to be high, or you may suspect that the chromatic number is actually equal to the clique number, but it is not true. There are graphs where the chromatic number is strictly higher than clique number. Can you quickly think of some example? Something which comes to your mind? Odd cycles. Odd cycles, you take a 5 cycle for instance, what will happen? The clique number is equal to 2. What is the chromatic number? 3, right? This pentagon. So clique number is only 1 edge because you don't even see a triangle here. So clique number is equal to 2. Biggest clique is 2. While you cannot color it using 2 colors. 1, 2, 1, 2. Here it should be 3, right? 3. Whatever way you try, it will need 3. But then you may think that this is just there. I mean, just one more than the clique number because of this odd cycle kind of things. This is what people initially asked, is it so? Are there graphs whose chromatic number is higher than clique number? So, but it so happens that you can actually construct graphs where you keep the chromatic number as a clique number at some point, some place, and chromatic number can be increased one by one, right? It can go to any height, right? Any large number, right? So this was, for instance, there are triangle-free graphs. Triangle-free graph means the clique number is equal to 2. There is not even 3 clique. But the chromatic number is arbitrarily large. There is this construction, so where we put 5 vertices here. This is 3, right? But now what you do is, I'll write say 1 dash, 2 dash, 3 dash, 4 dash and 5 dash, and this say 3 dash. 3 here 3 is connected 2 and 1, so this will also be connected to like this. Okay, and for every vertex I will do that. 4 is connected here. 1, 2, 3, 4, 5, right? Sorry, 4, 5. So this 4 is connected to this and this. So I will connect this and this to this also. That means for a vertex I, whatever neighbors are there here, that will be made the neighbor of this also, right? And then I will put one here, one single vertex here, and connect all these things to that, right? So I have to complete these connections here. Now you will see that it will take a little thought to realize that the chromatic number has gone up by 1 now, right? That can be an exercise. You can try to prove it, but I don't spend too much time on that now because our topic is special class of graphs. I'm just trying to motivate it, right? So what I have done is, so a construction from starting from a pentagon where the chromatic number is 3, clique number is 2, but I made what the chromatic number one more now, 4. But do you think I have introduced any triangle in this this thing? No, because that's the way I did it, right? Because triangle is not there here in the pentagon, but here I only connected to the things which are neighbors of its partner, right? And if a triangle formed, the triangle already was there, right? It take a little time to figure out that, right? But that I'll leave it as an exercise. My claim is that you haven't created any triangle in this construction, so it is still triangle free. Clique number is still 2, but you have increased the chromatic number by 1 without proof. But it's a exercise problem only, so you can do it, right? And now what you do is you take this entire structure and repeat the procedure. That means for each vertex you have a new vertex, so independent set. For I will introduce an I dash, and then I dash will have exactly the same set of neighbors as I, right? And then I'll introduce a vertex which is outside and connect to all those dash vertices, 1 dash, 2 dash, 2 dash. Like that you can keep on going. Triangle will never be introduced. It will remain triangle free, but the chromatic number will go up by 1 again. So you can keep on doing it. So that means you can reach chromatic number 1000 after some time. The only thing is the number of vertices will go up, like every time you're making it almost double plus 1, right? So that is going exponentially large, but the chromatic number is going up, but the clique number remains at this point. So the entire story tells you that the chromatic number has nothing to do with the clique number other than just getting a lower bound from that. It's just more than equal to clique number. That's it. The story ends there. But on the other hand, if you start constructing just with a paper and pen, you will find it a little difficult to do that, because you won't realize what is this chromatic number, is it increasing or is it decreasing. There should be some systematic method like this, right? And there were a lot of questions asked at some point of time about this kind of things. For instance, is it just triangle? If you suppose I make sure that there are not even small cycles, like 4 cycles, 5 cycles, forget about 3 cycles, 3, 4, 5, 6, up to 10 cycles I remove. So then is it possible that my chromatic number is not much, right? That means it will be 2 or 3 or something like that. Why do I think like that? Because that's a very natural thought. Because suppose you make sure that there are no small cycles. Now you imagine a very big graph, and you can think of sitting on a vertex there, right? And then looking around you. Can anybody tell me? So those people who have good visualization, can you tell me what you see around it? So you suppose you avoided cycles of length till 1 million. Maybe 1 million plus 1 cycles are available in the graph. The graph is too big. Maybe some graph of the something galaxy or something like that, right? So huge, too huge. But it so happens that you're sure that there are no cycles in the graph which is of length 1 million, right? And beyond that, maybe cycles are there, but very large cycles. That's all. Now you're sitting on one of these vertices and looking around. Then what will be your picture around you? Far, far, far. What will you see? It will be like you don't see any cycle anywhere. From you, the graph will be going forward, spreading around, but it will look like what? It will look like a tree, right? So he's saying that. I think many of you got the intuition, right? It will look like you may mistake that it's a tree, right? If you don't, nobody told you that far away there are cycles, but sitting on your vertex and looking around, you may see that you may think that it's a tree and you are the root of the tree, right? Because cycles are not there. So, but to color a tree, there is a simple strategy. Color your root by white and then the next layer of vertices by black and then white and black. You may think that you can keep on going. So, there are two colors only are required, right? And at some point of time, maybe some errors are coming, some mistakes in the end somewhere. So, you give some 3-4 colors maybe enough is what you think, right? But it so happens that even that is not correct. There are graphs with arbitrarily large, small cycles are avoided. That means the shortest cycle can be made a very large number, the length of the shortest cycle, and still you may get a arbitrarily large chromatic number for the graph. This is a very famous result of Paul Erdos, answered this kind of a question, because people are worrying about this kind of questions. Is it possible? You can imagine that if somebody sits down with pen and paper, it will be difficult to construct such things, right? Because you don't see the intuition where this chromatic number is coming from, right? You avoided the cliques. So the only concrete thing that you can kind of associate with the chromatic number is probably the clique, and probably these odd cycles. Right, but then that's only one more than the clique number. But the truth is that chromatic number cannot be controlled by any of these things, neither clique nor cycles. So it's just it can grow without bothering about what this clique number or chromatic number. So in this, when all this research is going on, naturally you may ask the other question. Okay, if that is the situation, what kind of graphs have the nice property of the chromatic number being equal to the clique number, right? May I ask that? Okay, forget about it. I understand, I gave up. So your chromatic number can become very big. But I want to know what kind of structure in the graph, what kind of graphs, special things in the graph can make sure that the chromatic number is equal to the clique number. Right, chromatic number and clique number coincide. So this is, I think this is a very natural question to ask. When this kind of research is hot, and then a lot of people are asking questions of this sort, right? What is this chromatic number? How do we? Is there a function which controls function of clique number which controls the clique chromatic number and all? So then, and we say no, there is nothing like that. Then we ask this question. Which kind of graphs have chromatic number is equal to clique number? So naturally, when you ask this question, the point is that the answer, I mean, it's not a good question. Why is it not a good question? Can anybody tell me why is it not a good question to ask? That chromatic number is equal to clique number. Characterize that class of graphs. Somehow it is not satisfactory question. The reason is that even if some answer you say, it will not give you any intuition about things. Reason is that you get a graph here, some graph G, I mean, whose chromatic number may be much higher than the clique number here. See, omega of G. But then what I do is, I maybe put a tail here, and then let's say this is K. I put a KK here, clique of cardinality K here. Just hang a clique of cardinality K here. Then what will happen? This new graph G1 has a clique number is equal to, clique number of this G1 is equal to the chromatic number of G1. Because you can color this thing and color this thing anyway with chromatic number. You know, with this long path, so this is the chromatic number is not going to increase here because you color it here, right, with the same number of same set of colors, and then you can color this also with the K colors, and then whatever color you see here, you keep coloring with the, suppose this was black, put a white, black, white, black, white, wherever you reach here, name that accordingly, that's all, because this you can color, you can permute the colors the way you want, right? So that means you don't need any larger number of colors here, right? Or otherwise, if you make it simpler, you can even cut this. You put a clique here and then. So that means the chromatic number hasn't increased here. The clique number is, I made it equal to the chromatic number. So then I say that look at this graph, right? And then this has clique number is equal to chromatic number. And then what is the structure of that? You know that there, you haven't done anything. You have just you have cheated here, right? You have just took an arbitrary graph, right, which cannot have any structure as such. Otherwise, it's like asking for general graph. You just put a tail somewhere and then put a clique, hanged a clique, hung a clique on the end. So it is like omega is equal to chi there, but what structure can it have? It's just that something is hanging there, is it? So it does not give a satisfactory intuition about it. That's not I'm asking. So you may ask a question, but then that's not what I want to know, right? I want to know especially what exactly is the reason for the chromatic number is equal to I. So I don't want to hear an answer that if you take any graph and some clique is hanging somewhere, so it will be equal to chromatic number and all, right? So we want something more like sensible. So so looking at this thing, you soon realize that you have to change the question somehow. But you have a question in your mind, you have to formulate the question correctly now, right? The question is very reasonable, but the way it is asked is not correct. So we formulate the question in a slightly different way. So we say that I want the chromatic number is equal to clique number, and that same property should be true for any induced subgraph of the graph. Not just for the entire graph, but also for any induced subgraph. So this kind of cheating will not happen. So because this is an induced subgraph now, so the question will come back to this, right? So then you are again asking, is chi of g is equal to omega of g, right? So everywhere, for every induced subgraph, your chromatic number is equal to clique number, right? Then you ask, is there some property? So that's a consistent thing. That means it's not that all on a sudden you made, due to some adjustment, you made the clique number is equal to chromatic number. That is not what I want. You can ask that question. I'm not saying that you should not ask. So I want to know that globally that phenomena should be captured in a global way, right? Not only for the graph, but also for all induced subgraphs of the given graph, we should have this property. Clique number is equal to chromatic number. These kind of graphs are perfect graphs. So G is perfect if for all induced subgraphs H of G, omega H is equal to alpha of H. So this is the first definition. So the question was asked by Claude Burge. When we say Burge, in graph theory, the Burge name has a special significance because they are a few of the main people who developed the graph theory itself in the initial days, right? Like Tutt, Burge, Paul Erdos, all those people are the key people who initiated the subject, pushed this subject in the beginning stage so far. So his question, he asked this question, and then he started thinking about it, right? So he called it perfect graphs. And when he started thinking about it, he realized a few things. He wants omega is equal to chromatic number. The clique number is equal to chromatic number. And what is this chromatic number? Can you see the chromatic number in terms of something else? So what exactly is a chromatic number as a covering problem? So you are trying to cover the vertices of the graph using something. What? What kind of things? Colors. What does a color correspond to? Independent set. So in a chromatic number problem, the coloring problem, so it is a covering problem. Coloring problem actually is a covering problem. Covering by independent sets. Actually each color class is an independent set. You are actually trying to find out disjoint independent sets such that these independent sets cover all the vertices. Each vertex of the graph should go to exactly one of these independent sets, one and only one, right? Sort. Each vertex should go to one color class. Each vertex should go to independent. This is exactly the question. In fact, each color is an independent set. So if you color it, then each color class becomes an independent set. When you remove the color class one after the other, what you see is that a set of independent sets, disjoint set of independent sets, covered the set of vertices. The other way, if you give me a set of independent sets which covered the vertices, you could have colored it. No, each independent set I could have colored. That will satisfy the situation because every edge now on two endpoints I will be seeing only two different colors now, right? So, it's essentially the independent set cover problem, the minimum number of independent sets to cover the set of vertices, right? So therefore, the chromatic number and clique number is the biggest clique. Look, independent set is the complement of that. It's the exact opposite of that, right? A clique is one collection of vertices where everything is connected to each other. Independent set is the other side of it in the sense of why is this sound coming? Is it because I'm keeping it wrongly? Do it, yeah? അങ്ങോട്ട് പോകാൻ പാടില്ല ആ ശരി ഓ ശരി ഇവിടെ നിൽക്കണമല്ലേ ഓക്കെ okay, I think this is a position problem. The position. The machine learning, right? It's but I think it is something else. So, okay, whatsoever. Let me see. Maybe if I don't move, it is better. So, see, look at. I'm trying to explain this problem more carefully. A clique is a collection of vertices where every pair of vertices is connected. Independent set is exactly the complement of that in the sense that a collection of vertices, nothing is connected there, right? So now one side you have the clique, the other side we are trying to cover using the complement notion, independent sets, right? So we know that from a clique, no independent set can take more than one vertex from a clique, right? So therefore, we need at least so many, right? As many vertices as there are in the clique. As many independent sets there are in the clique because a particular independent set cannot cut the clique in more than one point, right? Because if 2 points it's cutting, how it cannot be an independent set. So that's that complement notion and the covering using that complement notion, right? And then it is a bigger number and we are asking when is it equal, right? When is that natural lower bound becomes the equal to that, right? And now an interesting thing what you can do is you could have asked this question in the complement sense. That means you could have just gone to the complement of the graph and asked what am I asking? The same question can you formulate in the complement. What will the clique become? Clique becomes a independent sets in the set in the complement. Clique becomes an independent set in the complement. And the chromatic number becomes what in the complement? Okay, even if you don't tell a name, what exactly is that? No, it is the minimum number of. No, because in the chromatic number is a minimum number of independent set that cover the set of vertices. When you go to the complement, we tell it is the minimum number of cliques that cover the vertices. Actually, there is no difference. You may dislike to see that it's like when I am trying to cover the vertices of the graph using cliques. It's called clique cover number. Clique cover number. The minimize the number of cliques so that every vertex is in exactly one clique, right? And so you want to find the clique cover number, right? This exactly is like covering using independent sets because that is happening in the. But then there is a fancy name. It's called chromatic number because we can see it in terms of the colors, right? We can see it in terms of the colors. I hope you understood what it is, right? So in the complement, we see a different picture. The clique number less than equal to chromatic number will become independent set number less than equal to a collection of cliques, the minimum number of cliques in a collection of cliques that cover all the vertices. Structurally, there is no difference. One is an independent set, the other is a clique, that's all, right? So you just swap it when you this thing. So therefore, first thing you understand is that whatever structure you are talking about, when clique number is equal to chromatic number, there should be some kind of structure in the complement also, isn't it? Because there also some phenomena is happening, just that its independent number is equal to clique cover number, right? So in the first graph it is clique number is equal to independent set cover number, that means the chromatic number, right? So we have 4 parameters when we talk about perfect graphs. One is, do we have a duster here? One is chromatic number, the other is omega, the next is clique cover number, this is omega, and if this equation is true in G, this equation will be true in complement, right, isn't it? So that is the same thing, yeah.
Alpha is chi. It should have been chi, right, in the definition.
Yeah, alpha.
Sir, in the definition.
In the definition? Okay. Okay. Is it clear to you? So at this point you have to concentrate on these 4 parameters which are kind of interlinked. Omega less than equal to chi, while in the complement we see the same thing as alpha less than equal to k of G, k being the clique cover number, right? So let's say that if a graph satisfies chi of G is equal to omega for all induced subgraphs H of G, then we call it chi perfect, and then we call the other thing like alpha is equal to k for all H of G, all induced subgraph H of G. This is alpha perfect. So one is chi perfection, the other is alpha perfection. Any questions on this? It looks like the same type of phenomena, though it's different, but it's a complement phenomena. One is called the chi perfection, the other is called the alpha perfection. So the key point is that if chi perfection is there in G, then alpha perfection is there in G complement. It's not very clear, alpha perfection will be there in G also, right? So this is one thing which Burge observed initially. he found that when he tried various examples, various graph classes which satisfy chi perfection, he saw that the alpha perfection exists in not only in the complement, which is obvious, but in the graph itself. So somehow he realized that this chi perfection, alpha perfection come together. The chi perfection implies alpha perfection and the complement is a trivial statement. But what Burge observed is a very non-trivial statement, namely, it so happens that whenever chi perfection is there in a graph, alpha perfection is also there in the graph itself. We don't have to go to the complement, right? So he suspected that this chi perfection and alpha perfection cannot be separated. I mean, if one is there, the other should be there. This was his first observation, and he could not prove it. But he saw it in various classes of graphs, and he conjectured. So that means in G, if chi perfection is there, alpha perfection also there. Or if you say that another way of telling it is, if G is chi perfect, then G complement is also what perfect? Alpha is trivial, chi perfect. G complement is also chi perfect, because if G complement is chi perfect, the alpha perfection will come back in G, right? So if G is chi perfect, G complement does have alpha perfection, but that is trivial thing. But G complement as chi perfection is what he told. But if G complement is chi perfection, then alpha perfection will come back in G, right? So alpha perfection will be there in G. Chi perfection in G will imply alpha perfection in G, or chi perfection in G implies chi perfection in G complement, right? Or if this is true, then you don't have to distinguish between chi perfection and alpha perfection. You can just say perfection, right? Chi or alpha. I mean, it's you can define one type of perfection, chi perfection, and say that if G is perfect, G complement is perfect. Complement of it also is perfect. That's what you can say, right? So this is the first conjecture he made. This is called a weak perfect graph conjecture. Weak perfect graph conjecture. But the actual main thing he conjectured was the so-called strong perfect graph conjecture, which kind of tells you everything about perfect graphs, right? What does it say? It says that a graph will be perfect. That means chi perfect, let's say, if and only if it does not have certain kind of induced subgraphs. That's what he told. Before going into that, just let's see which are the simplest non-perfect graphs. I mean, you have already seen that. Simplest non-perfect graphs. Odd cycles. Odd cycles means not 3 cycles. 3 cycles are cliques. Three colors are required. The clique number is also 3. They are not the ones. But 5 cycles, 7 cycles, all those things are non-perfect. The simplest non-perfect, in the sense that there is some kind of minimality associated with that. If you remove a vertex, any vertex, or take any induced subgraph of it, they are all perfect. Because if you remove a vertex from the cycle, then you end up with a path, right? Or path or collection of paths. You can remove more vertices, but the cycle will go. But they are all perfect now, because for every piece it will be clique number is equal to chromatic number 2 and 2, right? If it just becomes single vertex, then it is 1 and 1, right? So therefore, what we get is that chi perfection is equal to alpha perfection. Some minimal graphs, if you look for, these odd cycles are the things. But when suppose I ask you for another example, can you tell me? Non-perfect graphs but also make it minimal, because when I say why I am telling minimal is, otherwise you will say that take an odd cycle and put a hang edge from it or something like that, right? So that is not very interesting, because you can make, this is not perfect, right? But we don't want that. Something trees, what is the clique number? 2. Chromatic number is also 2. Trees are not. Peterson graph has this 5 cycles, induced 5 cycles. Peterson graph is triangle free. It is the clique number is 2. It needs 3 colors. All these things correct, but they have these 5 cycles. See, so they are induced, right? If you take these vertices alone and delete the other vertices, you just get these 5 cycles, right? So they are not minimal, in the sense that they have already got our cycle inside. That probably that is the one which are making them non-perfect, right? So that is exactly what Claude Burge wanted to tell. He wanted to tell that all non-perfect graphs are non-perfect because of the presence of certain minimal non-perfect graphs in it as induced subgraphs. As induced subgraphs, not the word induced subgraph. Whenever we are talking about perfect graphs, it is not about subgraphs, it's about induced subgraphs, because subgraphs can be anything, right? So that is, we have to concentrate on set of vertices and take every edge which is present in that. It's induced subgraph. So the Claude Burge wanted to make an assertion that a graph is non-perfect because these kind of graphs are present in it as induced subgraph. One is definitely this odd cycles, because you know that if there is an odd induced cycle in the graph, it cannot be perfect, because why is it so? But that's by definition, because perfection is defined to be like perfection is there only if for every induced subgraph also that chi is equal to omega, right? So if you have an induced subgraph which is non-perfect, right, odd cycle for instance, then look, go there, and there 3 number of colors is 3 and omega is, that itself make this thing, right? So that's why it does not make sense to talk about Peterson graphs. You do have even smaller structure in it which makes it non-perfect, right? So because every induced subgraph should have that property of chi equal to omega, then only a graph becomes perfect. So odd cycle is present, then as an induced subgraph, then it cannot be perfect. But is there anything else which you can imagine that which makes a graph non-perfect? Anything else? From all this discussion which we have done, so there is some hint to look at. It's essentially the complement of that odd cycle. Can it be perfect? Sorry, can it be perfect complement to the odd cycle? Complement to the odd cycle, suppose chi perfection you can check, right? Complement to the odd cycle means, for instance, if I take a 5 cycle, what is the complement? It's again a 5 cycle. Pentagons, that's a very interesting thing. You know, K5, if you remove a cycle, then you get a remaining is also that self-complementary. It is self-complementary in the sense that these pentagons have complements of pentagons, right? So therefore you see the same thing, right? So the complements are also non-perfect, but then that's not a good example because the same thing. But if you take a 7 cycle and if you go to the complement, my claim is that they are also not perfect. So for instance, you can check chi perfection there. Tell me whether it's chi perfect or not. How do you check the chi perfection of complement of a 7 cycle? I mean, you take a complete graph on 7 vertices, remove that that 7 cycle from it. The remaining graph, my claim is that its chi is strictly bigger than omega. Who can tell me how to verify it quickly? Who can tell me? How do you check it? Hint is that to check the chi-perfection of the complement, you need to check what of the original? Alpha perfection of the original, right? But original is a simple graph cycle. So can you check whether it's alpha perfect? Means what is the alpha of a cycle on an odd cycle? 7 vertices, for instance. What is the alpha? I can, if you want a picture, I can draw it. Sorry. Isn't it? This is a 7 cycle. Can you see the independent set here, alpha? Sorry. Three only. That's all, no? In the complement, this will become a clique, okay? So the 3 is alpha here. What will be the clique cover number of this graph? Clique cover number means I want to cover all the vertices with cliques, disjoint cliques. But in a clique, how many vertices can be covered in this kind of a cycle? Just 2, because there are no triangles there, no? 2, 1, 2, there are 7 vertices, 2, 2 if you cover also. After 3, 1 will be left, you have to take a 1 clique then. So there will be 4. 4 cliques are required to cover the cycle, and then 3 only independent set. So it is bigger. So in the complement, this becomes the chi-perfection statement, namely the chromatic number is actually 4, while the independent set number is, the clique number is 3 only, triangle, right? So therefore it's not perfect, right? So that you can easily check what I am telling is, you take any cycle, this cycle is neither alpha perfect nor chi perfect. So therefore cycle's complement also is not chi perfect. So right. So the cycle is one such graph where chi perfection and alpha perfection comes together. Sorry, no, so does not exist at all, right? So the first statement of Burge was that if you had chi perfection, you will have alpha perfection also with it. But if chi perfection is not there in the cycle, alpha perfection should not be there, right? So they should something coexisting, right? So at least we did not prove it, but if he was correct, that should be correct. So therefore, you see cycles and its complements, both of them are what? Non-perfect. And essentially, the Claude Burge second statement is this. This is exactly these two things, namely cycles, odd cycle, not cycles, odd cycles. Odd cycle means 5, 7, 9 like that, odd cycles or its complements. They are present as an induced subgraph or not is the question which decides whether a graph is perfect or not. This is a very, very clear statement, right? There is he's saying that that will decide it, right? So a graph is perfect if and only if it either has does not have any of these things as induced subgraphs, cycles or its complement, odd cycles or its complement. In the perfect graph literature, it's called odd halls and odd anti-halls. Odd means 3 is not a problem, but 5, 7, 9, right, and so on, right? It's complement. So now I summarize what I try to tell here. The Burge gave 2 conjectures about perfect graphs. One is called the weak perfect graph conjecture. Second is called strong perfect graph conjecture. naturally the strong perfect graph conjecture is a very, very strong statement. It kind of tells you exactly what perfect graphs are, right? That's a final complete answer to what he was trying to figure out, and he conjectured it. And that says that a graph is non-perfect if these odd halls or odd anti-halls are present as an induced subgraph in them. That we know that if they are there, it should be non-perfect. But then he says that is the only way you can become perfect. Or in other words, if odd halls and odd anti-halls are not present anywhere in the graph as induced subgraph, then it has to be perfect. This is what he told, if and only if, right? This is the strong perfect graph conjecture. And the weak perfect graph conjecture told chi perfection and alpha perfection has to coexist. That means there is no way you can separate them out. There is no way you can get a graph where there is chi perfection but no alpha perfection, or the other way, alpha perfection but no chi perfection. If alpha perfection comes, chi perfection comes along with it. This is what he told, right? This was the weak conjecture, but you can see that if you have strong statement, weak statement is obvious from that. Can anybody tell me why? If the strong conjecture is true, the weak conjecture is not even necessary. It immediately follows from that. Right. Suppose your graph is perfect, right? This does not have odd halls or odd anti-halls. Now you go to the complement. Complement cannot have odd halls or odd anti-halls. Suppose the complement had an odd hall, then our original graph had an anti-hall, right? If the complement had an anti-hall, the original graph had a hall, right? But we told that original did not have it because of the symmetry of the things which are right, kind of. Symmetry means I'm avoiding the graph and its complement, right? So therefore, graph is perfect, then that property should be satisfied, that no odd hall, no anti-hall. The complement also will not have odd hall or an anti-hall. So if G is perfect, and by strong graph conjecture, strong perfect graph conjecture is, if it is true, then the complement also will have to be perfect. Then we don't have to worry about the other thing at all. The perfection will come. Right? The perfection means suppose you can start with perfect chi perfection or something like that, and chi perfection. So then you can see this sequence will be true, right? The chi perfection implies no odd hall anti-hall, right, in the graph. So in the complement you will it's again perfect. That means there is no odd hall anti-hall. That means it should have chi perfection. Then that means the original should have alpha perfection, right? In this way you can prove the first statement also. Is it clear to all of you, this juggling of these things? What I told is, if you prove the strong perfect graph conjecture, the weak will follow from that. Anybody who hasn't understood it here? Any questions? I can stop here and you can ask any questions what you are not clear. Yeah. Can you explain what? Minimum clique cover number. Minimum clique cover number means you want to cover the vertices of a graph using cliques. Every vertex, each vertex should be in exactly one clique. And how many cliques are required to do that? For instance, here you may take this, you may take this, you may take this, and now what you do, this is covered, these two vertices covered, it's covered, only one is to be covered. This should be taken separately. Yeah, K1, one vertex clique, two vertex clique is the edge, three vertex clique is this triangle, so right. See, not that we are trying to cover the vertices, not many edges will be left uncovered, right? Cannot. Clique number? Yeah. Clique covering number is 4 for that 7 cycle. Yes. 1, 2, 3, 4. right? But the independent set number is 3. 1, 2, 3, right? That's why it is. Any questions? Any concept which is not clear here? I guess. No, if you haven't understood, you can ask, because I don't know what level. Most of you are at different levels, I think, and I have absolutely no idea about how to bring everyone to some common level. So if you, the only way you can ask questions, whatever you don't understand, you can ask, right?
Sir,
Ah,
in this we have a peak number, the covering number is 4,
yes,
the independent number is 3.
yes.
If we subtract, we will get 3.
Click cover number is,
Plus 2, we get 7.
yeah,
The cycle number is 7.
yeah.
Cycle of 7 cycle. It is possible for all the graphs for
No.
all cycles.
No, it is not. It's just that because it's cycle, it happens, right? So there can be many other.
Only for odd cycles.
Only for. I did not get what you're saying.
This condition is satisfied for odd cycles.
Odd cycles, this condition is satisfied. Any odd cycle, because if you take its alpha, it will be n minus 1 by 2, while the other will be n minus 1 by 2 plus 1. Together it will be n, right? But in general, it is not true, right? The click cover, for instance, if you take a complete graph or something like that, its maximum independent set is 1, just 1. The click cover number is also 1. So 1 plus 1 is nowhere near your n, right? Yeah. So it has nothing to do with the, you cannot add them up and get the total number or something like that. Okay. So to summarize, up to now what we have done is this. We introduced a graph class called perfect graphs. I think we have motivated it well, why we should why Claude Burge might have asked that question in a particular background. And the definition is that a graph is perfect if and only if all its induced subgraphs, including itself, have the property that the clique number equals the chromatic number. So then in this context, we should know 4 parameters. Clique number, that's the cardinality of the maximum clique. Chromatic number, which is essentially the independent set cover number. That means the minimum number of independent sets to cover all the vertices of the graph. Third thing is the complement parameters, namely clique cover number correspond to the maximum independent set in the complement. That is the stability number or the independence number, right? People use both these words. Some people use stability number, the other people use, some others use independence number. Cardinality of the maximum independent set. And the chromatic number, which is actually the independent set cover number, right, correspond to the clique cover number of the complement, right? That is K, that's the 4th parameter. And then we told about chi perfection, namely omega is equal to chi for all induced subgraphs H of G. And the alpha perfection is alpha is equal to K, clique cover number of all induced subgraphs of G. And Claude Burge conjectured 2 things about perfect graphs. One is the weak perfect graph conjecture, where he told that the chi perfection and alpha perfection always coexist. You cannot separate one from the other. If in a graph one of the perfection comes, the other type of perfection also comes. And in other words, it's another way of telling is, if G has chi perfection, G complement also has chi perfection. Or in other words, we can say if G has alpha perfection, G complement also has alpha perfection, right? This is another way of telling it. That was a weak perfect graph conjecture. The other thing which is called a strong perfect graph conjecture is much more solid, right? It kinds of states what perfect graph is. It states that a graph is perfect if and only if certain kind of graphs do not appear as induced subgraphs in them. Which are those certain kind of graphs? They are called halls, odd halls and odd anti-halls. Odd halls and odd anti-halls. When I say hall, that is an induced cycle, right? Induced subgraph which is isomorphic cycle, which is 5, 7, 9 odd, excluding the 3. 3 is not a hall because it's not a hall. It's like you have already, if you want to imagine a hall here, right? There should be something empty, right? So, but triangle is not like that. It's filled, right? So you should think that in graphs there is no hole there. It's like as if it is a brick, right? You can't go to the other side because there is nothing more you can fill there, right? So therefore, 5 cycle, odd hole means 5 cycle, 7 cycle. Remember codeless cycles. Induced cycle means codeless cycles. There is no code, right? Because if you see, identify a cycle, you should not see any edge of this sort from some see this kind of edges only should be there. You should not see codes, right? These are the odd, these are the halls, right? Because if codes are there, that hall effect will not be there. No, if you try to jump through the hall to the other side, then what will happen? That code will block it, right? In that sense, hall. It should be really a hall, the complete hall. When you say that, okay, if there is a hall, why do you think that it's just that some code is blocking there, right? But you say if you will see that so hall, if you break that code also, finally, it should be a good hall, right? Odd halls or odd anti-hall means the complement of the halls, right? So these are the things which you should avoid to make a graph perfect. If they are there, they cannot be perfect. That's very clear because all induced subgraphs should have this chi perfection, right? And the halls and odd halls do not have, the odd halls and odd anti-halls do not have that chi perfection. I mean, chi is actually less than omega there. Sorry, omega is strictly less than chi there. So therefore, if they are there, definitely you cannot, that graph cannot be perfect. They are non-perfect. But the point is that if they are not there, that's the more non-trivial thing. They are perfect. They will have chi perfection and they will have this thing. So to decide the graph is perfect or not, you have to search through the graph for this kind of halls and anti-halls everywhere. And not that so easy because they themselves can be big. For instance, not that you can a polynomial quickly do that. That needs sophisticated. You can do it polynomial time, but recognition is possible. But it requires complicated algorithm. That finally it took so much time to develop all those things, right? So is it clear to all of you? Is it clear to all of you what this strong perfect graph conjecture and weak perfect graph conjecture is saying? Clear? Okay. So this is the story of the perfect graph conjecture to begin with. So and what Claude Burge did is he went traveled everywhere and he was giving talks and he was popularizing his questions, and I think within about 10 years or so the first conjecture was solved. I forgot exactly number of year. But there is a lot of competition to solve that question. Weak perfect graph conjecture was solved relatively faster, but the strong perfect graph conjecture resisted all attempts. It's not that people did not try, lots and lots and lots of people. I think all important graph theorists might have tried to solve it for around 50 years or so, 50, 60 years. But finally in the 2004 or so, it was settled. Strong perfect graph conjecture was also proved by Paul Seymour and Robertson, Thomas, and Maria Chudnowski, right? So a team of 4, I think. But it was a very long proof, almost, if I remember, around 200 pages of proof, very long and 5 years of effort, right? Very hard work. It took 5 years is what they say. So therefore definitely it's not something which you can teach in a class or something like that. So I mean, in the class we restrict to the first things. I mean, weak perfect graph conjecture only. In this class we will do the proof. That's a little later. I'll motivate it slowly, right? But going through many other classes and then I'll come to that. Because this weak perfect graph conjecture was proved by Laszlo Lowas, and I guess he was very young at that time, and then it came very nice, beautiful, in the sense that it's a very short proof. I mean, at least considering to the long proof, it's a 1.5 page proof, and it's very elegant, and it was after that was not the only proof. There was a proof based on anti-blocking polyhedra. I think Fulkerson gave one proof, but the story says that Fulkerson was working on this problem for quite some time, and but somehow he was convinced that it will not be possible to prove that, and then he was trying to get a counter example for, but then the young Lowas gave a proof, but very different approach, right? And then at that time, all these emails and all this social media, nothing is there, right? You cannot upload to archive and everything. They used to write letters. So then they wrote a letter to Claude Burge that I have solved your conjecture, and then Burge verified it, and he knew that Fulkerson is fully on this thing. He wrote a postcard to Fulkerson and said, unfortunately, the problem is solved. But so once he heard that this problem is solved, he was convinced now that the answer is positive, right? And he went back and checked his proof again, and he could also solve according to his method. Just that he got diffident at some point of time, thinking that it will not work, and he was trying to disprove it. So, but this is one story about it. So so a lot of competition. Even in the end, for the strong perfect graph conjecture, like there were other people who were working, other teams. I mean, when it comes to strong perfect graph, it was not just individual effort. It was like teams of 4 or 5 working together, and then trying. Competition was there. Very good people trying to get it done, right? But but then these people did it. So then, anyway, this is the introduction to perfect graphs. But when I say this thing, so initially, like when we define this perfect graph in a slightly contrived way, so because for every induced subgraph, this property should be there and all. It's not a natural thing which you usually see. Many other definitions are much more simpler, and this thing. Then still, why people were after this perfect graph thing? So it so happens that many of the well-known graph classes at that time happened to be perfect, and then this property which looked somewhat strange, right? That means every induced subgraph should have chi is equal to omega, was working out for all those graphs. So people thought that there should be something in it. So what we do is we will go through several of these graph classes and see why this chi equal to omega there. And for example, the easiest case of a perfect graph is bipartite graph. Bipartite graph is perfect. Can anybody tell me why it is perfect? No odd cycle. Yes, no odd cycle. Yeah, that way it's very easy to see. Suppose if you assume strong perfect graph conjecture, then you can see that there is no odd cycle itself. Forget about induced odd cycle. The complement of an odd cycle is also not there. Why is it so? Yeah, because the complement of an odd cycle, if it is 5, it is odd cycle itself. If it is 7, it's definitely triangles and all will come. I can prove that. But then you have to assume the strong perfect graph conjecture there. Yeah, but you can much easier before, I mean, without using this heavy theorem of strong perfect graph theorem, we can get it done. Namely, the bipartite graphs, what is the chromatic number? 2, right? 2 and what is the clique number there? 2, because there is no triangle, right? So 2, so 2, 2. So any induced subgraph if you take, that's again a bipartite graph. So therefore the same thing will hold. Sometimes it's possible that when you take an induced subgraph, the clique number may reduce to 1. That means when some isolated vertices are selected, then the chromatic number is also 1, right? So therefore you can easily check that bipartite graphs are perfect. So that is one good example, but easy example for a perfect class. Now let's look at the complement of a bipartite graph. That means, or in other words, we can check whether bipartite graphs are alpha perfect or not. Either we say our complements of bipartite graphs are perfect, or is it true that bipartite graphs are alpha perfect. Alpha perfection in bipartite graph means the chi perfection in the complement, right? Can you tell me why they are alpha perfect? What is alpha perfect? Alpha should be equal to clique cover number. What is the alpha of bipartite graph? That seems to be a little more.
You will be having, like in complement, you will be having edges on
Okay, let's keep alpha as alpha. Now we start with the other side. I mean, clique cover number. That is something. What is the clique cover number of a bipartite graph? Size of a biggest clique is also 2 only. So that means clique cover number, how much will be the? Yeah, you have to collect disjoint edges and try to cover the vertices. But how many you can select? I mean, I want a number. How will you? Yes. Matching. No, that is hard, because when you cover, try to cover the vertices with cliques of cardinality 2, that means edges. What you are seeing is matching. But then if you take the matching, you can take the maximum matching. But when you take the maximum matching also, it may so happen that you may not match everything, right? Then what will be my clique cover number? Using, I already given enough information, just give me a formula in terms of this matching and all. So that should be M, the maximum matching, plus what? Because the when I take one edge, okay, two are covered, another edge, 2 are covered. So now maximum matching will cover how many? 2 times cardinality of the maximum number of edges is covered. The remaining vertices are, because there is no more edge to pick up, no? I mean, those people who have taught you vertex cover and all those things might have told you that once you remove a matching, what is left is what? It is a? Once you remove a matching, both the endpoints of all the edges of a maximum matching, not matching, maximal matching or maximum matching, what is left? It's an independent set, huh? Yeah, so then you have to select all of them, right? Because they are independent set. Now you have to cover one by one, right? With one vertex set. So that is 2 into, or no, n minus 2 into n. Correct? Agreed? Because this many singletons and this many edges. 2, 2, 2, 2, 2, 2 is here, and then this is n minus m. But how do I show that this is alpha of G? This is the clique cover number, K of G. Anybody, can you find a link from this to this? Anybody? See, listen to this question. This is already for bipartite graph, this alpha perfection is getting interesting. Alpha perfection of the bipartite graph asks for proving that the clique cover number of the bipartite graph, any bipartite graph, is equal to alpha. Alpha being the biggest independent set cardinality. So I started with the clique cover number, and as somebody suggested, because even triangles are not there, there are only 2 types of cliques, namely the edges and singletons. So it's better to collect as many edges as possible. That is because you want to minimize the number of cliques used, right? It's better to select as many edges as possible, right? Isn't it? So if you are collecting as many edges as possible, that is essentially the maximum matching, because disjoint edges, right? The cliques are disjoint. So that kind of leads to maximum matching. So maximum matching is selected, but then what happens is now you cannot take any more edge. So you have to take singletons now. How many singletons you have to take? Depends on how many vertices are left. That is n minus 2m, right? Because 2m is already covered, n minus 2m. Then I added m and n minus 2m, that is n minus m. But why is this n minus m equal to alpha? From all the things which you have seen in earlier classes, those people who have listened to the vertex cover class and all carefully might be knowing a relation between n minus alpha and what? N minus alpha is what? Yeah, for bipartite graph. For other graphs also? N minus alpha is equal to the vertex cover number for any graph. So n minus m is what? M is what in bipartite graph? Cardinality of the maximum matching. What is Koenig's theorem? Koenig-Agarwal theorem, right? Well, it says that this is the beta of G, namely vertex cover number. So n minus the vertex cover number is same as n minus alpha, but n minus m, because m is equal to this, m is the maximum matching cardinality. This is essentially the vertex cover number, minimum vertex cover cardinality in bipartite graphs. So n minus minimum vertex cover number is equal to this, because minimum vertex cover and the independent set is related, no? Because if you add them together, you have to get n, right? Minimum vertex cover cardinality plus the maximum independent set cardinality is equal to n. Okay, I hope they have taught minimum vertex cover right here. Minimum vertex cover, one key property of the minimum vertex cover, I mean everybody who works on minimum vertex cover uses this idea that minimum vertex cover, if you remove the minimum vertex cover, what is left is a maximum independent set, right? So that means it comes in pairs. Vertex cover and independent set comes in pairs. So if this is a minimum vertex, if it's a vertex cover, the remaining is an independent set. Minimum here, maximum there, kind of, right? So if you add them up, then you get n, right? And so Koenig's theorem, Koenig-Agarwal theorem, the bipartite graph has a speciality that the matching, cardinality of the maximum matching is actually the minimum vertex cover there, right? And that is what I have used here, n minus m, I replaced by n minus MVC size, cardinality of the minimum vertex cover. I don't know what is the notation they were using. I wrote beta for minimum vertex cover cardinality. N minus m is equal to n minus beta, but this n minus beta is actually alpha, right? That is, we are connecting to one theorem about bipartite graph, namely Koenig-Agarwal theorem, Koenig's theorem. That is m is equal to, cardinality of the maximum matching is equal to minimum vertex cover cardinality. And then we are connecting to the observation, namely minimum vertex cover when you remove from n minus beta is equal to alpha, namely it goes to the independent set. So that way you can show that this alpha perfection is also true in bipartite graphs. If you haven't understood it, I think I will suggest that you go through this argument in your mind later, because that will help you to understand the structure of these things, many parameters together, beta, minimum vertex cover cardinality, maximum matching cardinality in bipartite graphs, right? All those connections are like you can, while going through this proof, you will get to it. You can fix it in your mind, because these are things which are very, very interrelated, all these things, right? Though they all have different names, somehow they are structurally very close things. Okay, so this is about bipartite graphs. Second, so I have now given you an example of a perfect graph, namely bipartite graph. Then I also checked the complement of the bipartite graph and verified that it is perfect, right? Because I am just checking chi perfection, but when I am checking chi perfection of the complement, I am checking the alpha perfection of the original. That's all, right? Now let us take another class of graphs called line graphs of bipartite. What is a line graph? Anybody who knows what is a line graph here? Line graph is a very usual construct to move from edge set to the vertex set. In the sense, what you do is if you see a graph, suppose this is a graph here. So let me number the edges here: A1, E1, E2, E3, E4, E5. Now from this graph I will get a new graph which is made like this. For each edge I will create a vertex here: E1, E2, E3, E4 and E5. There are 5 edges here. I put 5 vertices corresponding to each edge. I associated a vertex. Now E1 should be connected to this edges touching this, right, E2 and E5. So E1 should be connected to E2 and E5. Agreed? Because E4 also. Yeah, E1 is. Yes. So this E1 is connecting to this and this, right? So because they are sharing endpoints with that, whatever other edge it is sharing an endpoint, you connect it to that. And now let's take E2. E2 is connecting to E1 already, and E5 it is connecting to, and then and E3. Now E3 is connecting to E2 and E5 and E4, right? And E4 is connecting to E1 and E5. Yes. What is not connecting now? This E4 and E2 should not be connecting. Yes. There is no edge there, right? Because E4 and E2 are disjoint. And E1 and E3. This edge is not there, see? Because they are not touching each other. And what? E5 is touching everybody. Agreed? So this way, given any graph, what you can do is number the edges first. Corresponding to each edge, you introduce a vertex. And now look at each edge and which are the other edges it is incident on this edge or through this endpoint or this point. I mean, with sharing an endpoint with this, right? Then you can construct a graph. That's called the line graph or the original graph. Suppose this is called G, then this will be called L of G. Line graph of the original. This is a line graph construction, right? Now I can ask you a few questions like, okay, suppose if I take a complete graph Kn and take the line graph of Kn, consider L of Kn. How many vertices are there in L of Kn? N C2, because each edge will become. Now, how many edges are there in L of Kn? Okay, forget it. I mean, let's ask this question. In L of Kn, what is the degree of each vertex in L of Kn? Because it's connecting to other edges, take an edge, connecting to other edges through both endpoints, right? So how many others are there? 2 times? 2 times n minus 2. Is it clear? 2 times n minus 2. Now, yeah, you can try to construct line graphs of various things. So tell me a graph whose line graph is the same as that. I mean, isomorphic to that graph itself. complete graph will have a very huge line graph. If you take an n kn, then n choose 2 vertices are coming. Tell me one line graph where if you construct the line graph, you get the same thing. Huh? What? 3 cycle. Not only 3 cycle, all cycles, right? If you take Cn, then you get the edges are same as the number of vertices. You put it's like imagining that in the middle of a cycle you have put an edge. That's all, right? Okay. Agreed. So therefore cycles are on. But tell me one class of graphs where if you take a line graph, you will get the same type of graph, but it shrinks or it becomes smaller. What? So if you keep on taking line stuffs, you will see the same type of graphs that keep on shrinking. Path. For instance, if you take a path, you still get a path, but the point is that you will get a smaller path and it will keep on shrinking, right? Finally, it will become an edge and it will disappear. Line graph, if you keep on taking line graphs, right? So this line graph construction is interesting construction. So for so what usually many theorems which are stated in terms of vertices. Right? Suppose you know a statement about some graph theoretic statement about the vertex set of a graph. Now, if you want to make a statement about the edge set, sometimes this can be used. I will tell you one example. Suppose I know that the chromatic number of a graph is less than equal to 2 times delta plus 1, right? The greedy algorithm. Maximum degree plus 1. So do you know that? So if the chromatic number of any graph is at most the maximum degree plus 1, just the greedy algorithm if you do. Give a vertex a color, and then every time when you are about to color a vertex, you just look at the already colored neighbors and use a new color, right? So then you keep on doing it, and then every time the worst case you may see a vertex, all its neighbors are colored differently, but only delta maximum degree number of neighbors only are there. You may have to use only one more color. So that's the greedy algorithm. So then suppose now I ask this question. I color the edge set of the graph instead of the vertex set. Now the edge coloring. The edge coloring, like whenever 2 edges are incident on the same vertex, that means they are sharing the endpoint, then they should get different colors. This is the edge coloring problem. So how does this statement translate to the corresponding edge coloring statement, the chromatic index, namely the minimum number of colors to color the number of edges is less than equal to. So you have to construct the line graph, right? And then it's a vertex coloring there. But then now you have to see what is the maximum degree of that graph in terms of the original maximum degree. What will you get? An upper bound only is required.
Maximum number of an edge having the maximum.
How big can it go, the maximum degree? Because now a particular edge can see on both sides, no? Delta minus 1 edges may be going from this end. And the other end also you may have delta minus 1. Yes, something like this. Right? Here I may see how many? Delta minus 1 here. Here delta minus 1. So total 2 into delta minus 1 plus 1. Right? 2 into delta minus 1 plus 1. So you can write something like this, right? So I just gave you an example how you use this to translate the statements about vertices to the statements about edges, because you can construct it and convert them into vertices now. No, you have to does not mean that this is a best statement or something like that. You know that there is a theorem called Weissing's theorem, which says that this much is enough for if you try to edge color, right? But then that requires more proof. But this is very easy. You just convert it, right? The greedy algorithm can be converted. I just told you that line graph sometimes can be useful to quickly convert like a statement which you know about the vertex set of the graph can be made use of to get a statement about the edge set, because now the edge set becomes the vertex set, right? As such, line graphs are much more structured than the general graphs, because they are all graphs cannot be line graphs, right? Some graphs can be, I mean, the question of line graph recognition means you are given a graph, now you ask, is there some other graph such that this is the line graph of that? This is isomorphic to the line graph of that, right? Okay, now what are we interested in now? We are back to the perfect graphs. So we are interested in the line graphs of bipartite graphs. Line graphs of bipartite graphs. So our claim is that line graphs of bipartite graphs are perfect. Can anybody verify this? At least chi perfection, can you verify? Why are the line graphs of bipartite graphs perfect? Chi and omega we should understand.
Trying to get a forest, you might get a forest.
When you construct a line graph, no. Actually, first you should think, suppose I take a bipartite graph G and I construct a line graph of it. What will be the clique there? What should correspond? What will become the maximum clique? Where is the maximum clique coming from? Huh? Maximum? The edges corresponding to the maximum degree vertex, right? Because see, if you see in the original graph some structure like this, right? Now in the line graph, see, we will be introducing a vertex for all these things, right? Now I can pictorially put this thing. In the line graph, this all will become vertices, but they are all sharing this common thing, right? Therefore, we will have connections everywhere, right? This will be a clique because pairwise connection will be there, right? So therefore, whenever you see a maximum degree vertex, all those edges, that means delta number of vertices in the line graph will form a clique, delta clique. There is one situation where actually a clique will come from a different structure than a degree, I mean a vertex, same, I mean the edges going out of the same vertex. What is the other situation where you can get a clique? Of course, if there is a triangle, the triangle may translate to a triangle, right? But in all other cases, like all the cliques will come from some situation like this, a particular vertex holding all those edges, then all those edges will be pairwise adjacent. You have to think about it a little bit. Is there any other situation you can get a K4, for instance, other than coming from the same vertex? The edges coming from, 4 edges coming from the same vertex can actually become a 4 clique in the line graph. But is there any other way a 4 clique can be formed? Doesn't look like, right? You may have to prove it with a little effort, but I think it's not very difficult, right? That means the maximum degree vertex, if you look at in the graph, the edges which are incident to that maximum degree vertex, that delta number of edges will form a delta clique. And that is the clique. That's the clique number of the bipartite graph, line graph of the bipartite graph. Now, what is the chromatic number of the line graph of the bipartite graph? Chromatic number means you have to color or cover with independent edges. Coloring is also fine. Coloring is fine. Coloring is better. Coloring the vertices of the line graph means coloring the edges of the original graph. So it becomes an edge coloring in the original graph, right? What is that? It is maximum matching will only form a color class, one color class. But actually you might have learned a theorem which gives you some information about the the chromatic edge chromatic number, that means chromatic index, or the minimum number of colors required to edge color a bipartite graph in such a way that no two adjacent edges incident to the same vertices will get the same color, right? That is also a conics theorem. No, that's also a conics theorem. It's called it's equal to the maximum degree only. Maximum degree. You can there is I don't know. I don't want to get into that because that's related to this Weissing's theorem. In general, you only need delta plus 1 colors to edge color a graph. But in bipartite graph, you need delta colors. Delta colors are required, delta colors are enough. So it is delta, the minimum number of colors required to color the edge set of a bipartite graph in such a way that no two edges incident on the same vertex get the same color. It's exactly delta, and that's the maximum degree. So this statement converts to our Kuiper-perfection here in the line graph of because the delta happens to be the maximum clique, max clique, the omega in the line graph, and the same delta happens to be the chromatic index of the bipartite graph. That means the chromatic number of the line graph. So both are delta, right? So this is, I guess, this much is enough for. I mean, we have it's time. We started a little later than 11:30, so it's 1.5 hours. But so the what I'll summarize the last part. Actually, bipartite graphs and complements of the bipartite graphs are perfect is what we did. To checking the Kuiper-perfection of bipartite graph was a trivial thing. Complement of the bipartite graph required a little more thought, but we connected the conic Gagavai theorem. That means maximum matching is equal to vertex cover, minimum vertex cover cardinality, and through that we connected that thing. And then we considered the line graph of the bipartite graph. Line graph of the bipartite graphs, we just checked the Kuiper-perfection that chi of the line graph of the bipartite graph is actually the edge chromatic number of the original bipartite graph we started with, and that is actually delta. That's the maximum degree of the bipartite graph. That's another theorem. That means you need a proof of that, but if you have already seen it, fine, because I don't want to divert into that, right? So yeah, it will take a little time to introduce all this. But that theorem, if you use, it is the maximum degree there. But on the other hand, the clique number there, omega, of the line graph of the bipartite graph is actually the maximum degree of the bipartite graph from where it came from. So that's also delta. So delta equal to delta. There we connected another theorem that you should understand. So this is probably one reason why people who initially studied perfect graphs became fond of it, because they saw that many of the at that time very important well-known theorems, right? At that time the graph theory was not this developed, maybe it was around 50 years ago, right? All those theorems which they teach usually in class and all, right, was getting connected in this, trying to prove the perfection of Kuiper-perfection or alpha perfection of various special classes of graphs, bipartite graphs or line graphs of bipartite graphs. Well, it is kind of will like inspire some curiosity, right? Why this is interesting that this proving this Kuiper-perfection is equal to alpha perfection. We are going through the things which we already know, right? So maybe why this is trying to generalize all these statements which I already know about these things, and then that probably was interesting for the initial researchers to study this thing, right? Because when you look through the several special cases of that, they were finding curious connections, right? They're actually going through things which they already knew some as theorems associated with other people, right?